Well, I would like to thank you, the organizer, to invite me to be here. This is my second favorite place, so I really enjoyed this visit. Well, I think it's not this topic is not related with the last one. I mean, it's not related with stochastic differential equations or something like that. But I will talk about what is this work that is a joint work with Juan Carlos Pardo and Victor Rivero from CIMAT. And I will try well, I may not be technical. I mean, just I give some ideas of the main result that we have and some pictures, and we'll draw some the pictures to show you what is the idea behind of this work. Well, in this talk, principally, we present a necessary and sufficient condition for the existence of recurrent extension of real cell similar Markov process. Basically, our main result ensures that real cell similar Markov process with a finite heating time at the point zero has a recurrent extension that leads zero continuously if and only if the Markov additive process associated via Lamperti-Kiu transformation satisfies the Kramer condition. Or you can see there are phrases that we highlight with blue. That this means the real cell similar Markov process, Markov additive process, Lamperti-Kiu transformation, and Kramer condition. This is the four things more important in this work. So my outline on my talk is I will give some preliminaries, main result, some examples, and how I said before, I will not be technical in this talk. Well, the background: Lamperti in 1972 studied the structure of positive cell similar Markov process and posed the problem of determining those positive cell Markov process that agree with a given positive cell Markov process of the time the latter process first here zero. Well, first, a cell similar Markov process is a process that satisfies the following. This we have this is equal and low to the process xt, but with the starting point here. This Cx for all C positive, and where this number alpha is the index of similarity. In 1972, Lamperti showed that for the first heating time of the point zero, we have three possibilities. T0 is finite, or T0 is infinite. T0 is finite, and the point zero is reached continuously, and T0 is finite, and the point zero is reached by a jump. This is for all x positive. So the thing here is that if we have a positive sensing Markov process, we can reach the point zero continuously. We can reach the point zero by a jump, and never could be. But in this case, we are interested what is the process that we can agree with this one. I mean, this is not studied here, but for this one, I mean, it's the same trajectory, and after could we go? Could be here, jumps, and after could we go? that is the question that Lamperti posed in that paper. And he answered this question to the special case of Brownian motion. In that case, he showed that we have three cases. The reflecting, I mean the Brownian motion that is reflecting the point zero. The absorbing Brownian motion, that means that the Brownian motion is absorbing the point zero. And another one that is extended by considering this measure. That we have three possibilities. So that problem was solved, at least on the Brownian motion case. And in the 90s, Bullia-Piala used the Excursion theory to study the general case. I mean, the general case, I'm saying that it's a positive Celsius Markov process, but not necessarily a Brownian motion. And in that case, provides sufficient condition to the resolvent of the positive Celsius Markov process for the existence of recurrent tension that leaves zero continuously. That is that work. The main contribution of Bullia-Piala to this problem is that it admits a unique entrance law, which there exists a unique recurrent Celsius Markov process, which should turn out to be an extension of positive Celsius Markov process after it reaches zero. In 2005, Rivero provided a simpler sufficient condition for the existence of short recurrent extension, a more explicit description of the entrance law. The sufficient condition found by Rivero was determined in terms of underlying Levy process and the so-called Lamperti transform. The Lamperti transform says the following. For Celsius Markov process, until the first time that is the point zero reaches, we can see as an exponential of Levy process time change. Here is a Levy process. She is a Levy process. And this random time change, tau, is the infimum of S positive, show that the integral of 0s exponential alpha u du greater than d. In that case, it's always possible to express positive Celsius Markov process an exponential of random time change, the Levy. In that case, in the case where the point zero is never reached, the Levy process goes to infinity. In the case that is reached continuously, the Levy process goes to minus infinity, and in that case, the Levy process oscillates. In this talk, in this work, we only interested in this, and this two. This is not. Will be interested because one of hypotheses is that the point zero is always reached. That is the idea. In 2006 and 2007, they provide in separate works a necessary and sufficient condition for the existence of that recurrent extension that leaves zero continuously. What the condition that they gave, well, is that the point zero is always reached and admits a positive semi-Markov process, admits a Celsius recurrent extension that leaves zero continuously if and only if the Levy process in the Lamperti representation satisfies the so-called Kramer condition. The Kramer condition for Levy process ensure the existence a number theta positive, showed that the expected value of theta G1 zeta greater than 1 is equals 1. This quantity is the time where the process is killed. So so we will give, or we'll try to give this condition in the general case. What I mean in the general case, well, the general case is considering not a positive Celsius-Markov process, but a real Celsius-Markov process. I mean, a process taking values in R, not just in the positive part. So, a real Celsius-Markov process, as I said before, is a process that which satisfies this scaling condition, and we will denote by T0 as before, the first heating time of the point 0. And examples of this kind of process, well, the first one is the classical alpha stable process. The alpha stable process is the first classical example of a real Celsius-Markov process. And second one, second example is the alpha stable process conditioned to avoid 0, which we can find in this paper, shown in 2013. There, they consider an alpha stable process, an invariant function h, and use the dupe transformation to construct this process as an example of real Celsius-Markov process. And recently, we have the alpha stable process conditioned to be continuously absorbed at the origin. That is more or less the main idea. Consider an invariant function and to reverse and to try to reach the point 0 continuously. In the rest of this talk, we will assume that the point 0 is always reaches. And we will say that recurrent extension, as before, is a Markov process that agree with the Celsius-Markov process until the reach the point 0, in which the state 0 is regular and recurrent state. Well, as mentioned before, we have the Lamperti transformation for positive Celsius-Markov process, but something that we need to give is the same thing, but in a real case. In the real case, involves something called Markov additive process that is similar to Levy process in the following sense. It's a Cadillac process. In fact, two processes. One of them is a continuous time Markov change, and another satisfies the following. Given JT equals y, the pair that this increments and this point is independent on the original standard transformation, standard filtration, and has the same distribution that we start again. That is the meaning that when I say that is almost a Levy process, and moreover, this kind of process, the Markov additive process, MAP for short, can be represented in the following way. That means the following. We have, I will draw, we think state space is equals -1, 1, and this is the Markov change. This is 1, jumps, here, go, here, go, etc. And the process, she goes as a Levy process. this is a Levy process, and the time that the Markov chain jumps, this jumps also. And this behavior is like a second Levy process, and so on. We have the third one, another Levy process. The important thing here is that this and this one are equal in low. This is the size of the jump. This is the size of the jump. That is the main idea of this representation. I mean, we have a Levy process, a starter Levy process. The sign of the this Levy process is given by this Markov change. When the Markov change jumps, the Levy process jumps and change, and another Levy process. And when the Markov change jumps, change another Levy process, and so on. And the all Levy process here are identically distributed. So that is the idea. For that reason, I say that the size of the jump, well, in this case is they are any random variables. I mean, the only thing that we need to do is give this. It's not a rule. In the case of when we try to relate with the original real Celsius Markov process, it is just the last part, the real Celsius Markov process divided by the original before to jump. In this case, is I don't remember how can I say that. That's a good question. Yeah, but in general, we can propose that. Okay, I would think about it. I don't remember now. Well, why is important to give this representation? Because we can define the same thing that Laplace exponent or the characteristic exponent or Levy process, considering all of these objects in the following sense. We consider the rate matrix of the change Q, the Laplace exponent Levy process Xi I, and we define Fz by the diagonal of the Laplace exponent plus the rate matrix multiplied element wise by G, where is the generative function of the size jumps. This matrix satisfies the following. If you remember that the Kramer condition is more or less the same thing. So the Kramer condition that I will give, or we will give later, is in terms of this matrix exponent F. Some assumptions. Well, the mass appearing in this talk is like this. The state space is -1, 1. And J is an irreducible Markov chain with equilibrium state distribution pi. And is in the similar case of Levy process, we can consider the dual of a map that we construct in the following way. Is this Markov additive process which satisfies the following, where f hat z is given by this matrix, and the Q intensity of matrix of the modulating Markov chain on this state space is given by this expression. Something that we can show is that the matrix exponent of the dual satisfies the following identity. I mean, always it's possible to compute the matrix exponent knowing the elements of the stationary distribution and the the matrix exponent F. Well, another important thing in this construction is something called the Wald martingale. The Wald martingale is used to give a time measure of the process. How can construct this? Well, we can choose in the right engine vector of this matrix, satisfying the following, and normalize it by this expression. And the martingale, or the Wald martingale, is given by this expression. Is the exponential of this quantity. B is this right engine vector, and kappa z is the real simple engine value that which exists by Perron-Frobenius theorem. And in that case, we can consider this Wald martingale. So this martingale is a unit muon martingale with respect to the original filtration and in any initial distribution. So in that case, we can define the change of measure given by this expression as usual as is given in the Levy case. Under P gamma, this process, the original one, is still a map, and the matrix exponent on this process is given by this expression. This can be shown considering this Wald martingale. In the last element on this construction is the Lamperti-Kiu transformation. That is the same thing that we said before. The different thing that we have map. I mean, this is a map in that case, and the process that says what is the sign, this up and down, is given by the Markov change here. You remember when it's positive Celsius Markov process, this part it doesn't appear, but in this case, this is that controls the sign of the behavior of the region of the Markov process. Well, finally, the excursion measure, that is an excursion, well, that is a measure that satisfies the following three properties. This is carried, or this support is given by all trajectories that the process which are killed at the first time that hit that reach point 0, satisfies the following Markov property, and we consider this additional condition. So we will say that N is self-similar if satisfies the following property. That is we consider the excursion measure of this kind of trajectories is the same thing that we consider, or the original one multiplied by these constants, where this constant gamma is called the index of self-similarity of N. Well, something that Buré-Piala and Rivero prove is that any positive Celsius-Markov process for which 0 is regular and recurrent state either leaves 0 continuously or by jumps. We can prove the same thing considering a real Celsius-Markov process, not just positive, and we have the same result. I mean, we have that our recurrent extension of the real Celsius-Markov process must to leave 0 continuously or by jumps. Well, our main result says that the following, but the first thing that we have to do is define what is the Kramer condition and for the maps. The Kramer condition for the maps says the following: there exists a Z0 positive shot that the metric exponent is well defined in this interval, and there exists a theta positive and less than this point, and show that the eigenvalue evaluated in theta is equal 0. The value theta is the Kramer number. It's called the Kramer number. We will denote the p hashtag by the p theta. You remember p theta is the measure obtained by the Wald martingale. In that case, we will denote by p hashtag, where theta is, as before, satisfies the Kramer condition, and we will denote p hat hashtag. It's dual of the map. And finally, we will denote by I the exponential functional of the map. Our main result ensures the following. For real cell Siemens Markov process with index alpha positive, which hits the point 0 in finite time, we denote by this expression the map associated and to this process via the Lamperti-Kiu transformation. Then the following conditions are equivalent. There exists a Kramer number, theta, between 0 and the index of cell similarity. If this occurs, we can obtain that there exists a recurrent extension of this process that leaves 0 continuously, and show that its associated excursion measure from 0 satisfies the following and the following expression. We can characterize the entrance law associated with this extension. With this main result, we can generalize the Ribero's result and the general case. I mean, with the real cell Markov process case. This is our main result in this part. Finally, we have some examples. One of them is the stable process. I mean, I will give some examples when it's possible to compute or to ensure when it's possible to obtain the recurrent extension. And the first one is the stable process with index alpha between 1 and 2. It's well known that in this case, the alpha stable process reached the point 0. In other case, it's not possible to reach the point 0. In the one of our hypotheses that is the point 0 is always reached. So in that case, we can write the character exponent in the following way, where beta and C plus and C minus are given by this expression, and rho is the positivity parameter, and rho hat is the 1 minus rho, the positive parameter. The map associated of this stable process here at the first hitting time, the point 0 via the Lamperti-Kiu transformation satisfies the following. It can be possible to compute the matrix exponent explicitly. In that case, we can find this in this paper, Kuznetsov and all, the 2014. The matrix exponent is given by this expression. It can be expressed by using the gamma function, and it can be proved also that the determinant of this matrix exponent satisfies the following. In that case, we have that the map, if this is 0, we can find the Kramer number. In that case, the Kramer number is equals to 1 minus alpha. And in that case, 1 minus alpha satisfies B positive and less than alpha. So in that case, we can ensure that there exists a unique recurrent extension that leaves 0 continuously. The second example, that is the dual of a stable process. Well, here is we call dual of the stable process in the following way. Consider the stable process consider the stable process, alpha between 0 and 1. But in that case, the point 0 is not reached, right? I mean, it's something like this, but never is the point 0 reached. So we consider its map associated via the Lamperti-Kiu transformation, and we will take the dual because the original one goes to infinite, and if we consider the dual one, this goes to minus infinity, and this is the idea. We associate the original, consider the dual, and Lamperti-Kiu transformation. So we apply again Lamperti-Kiu transformation and obtain another process. And this process, it's possible to reach the point 0 because the map satisfies the following. The following. So this is possible to reach the point 0 when alpha is between 0 and 1. In that case, we will work with this process. So we can show, we can do some computation and to give the stationary distribution of the Markov change J, and satisfies the following. And using this identity, you remember this identity as shown before. What is the f hat? What is f hat? F hat is the metric exponent of the dual of this one. In that case, we can show that this is the expression of the metric exponent of this process, and the determinant of this matrix can be shown that is this expression, implying that the Kramer number is theta equals 1 minus alpha. So our theorem ensures that the relatively similar Markov process has a recurrent extension if this is satisfied. But if we want to, this is the Kramer number, must be less than alpha. So that implies that alpha must be greater than 1/2. So only in this case we can ensure that the existence of recurrent extension of this process. In other case, we cannot ensure that. Well, this process that we construct on this way is concise with the given by Cipriano in its paper in 2015. It's almost the same. And the final example is the spectrally negative case. I mean, I said that we consider the Markov change that always has an equilibrium, stationary distribution. In this case, we consider, let me draw another pictures. And the spectrally negative case, we don't have positive jumps, so the process behaves like this, and the way to reach the point 0 is continuously, because we have this hypothesis. From the Lamperti-Kiu transformation, it associated map also has no positive jumps, because it's the same thing, but random time changed by an exponential random time change. It's the same thing that is. So it always satisfies has no positive jumps. Therefore, the range matrix of the Markov change, J, is given by this. I mean, the Markov chain doesn't jump up, just jump down. And we will write, for simplicity, Q plus to this rate. Furthermore, since the process X has no positive jumps, this this random variable that is the jump of the process is equal 0. It can be shown that the metric exponent of this satisfies the following identity, where where this expression is given by psi1z minus q plus is the Laplace exponent of xi, a spectrally negative Levy process, killing exponential time with parameter q plus, which is associated via Lamperti transformation to the process x killed at the first time it is at the point minus infinite 0. Well, the determinant of this matrix is equal 0 if and only if one of two of these quantities are equal 0, one of them. In other words, this map satisfies the Kramer condition if and only if its associated Levy process satisfies the Kramer condition. If we denote by these quantities the largest 0 of the Laplace exponent given before, we can ensure that it always is possible to, well, if this quantity in this case, then the second one, I mean, because this is the process that will give what they will permit to reach the point 0, and this quantity is between 0 and alpha. It's always possible to have a recurrent extension that leaves 0 continuously. Well, that is basically my talk, and thank you for your attention. Multidimensional case, this extension, you mean? Well, we need to define a general, well, and a little bit general. We give that little bit general definition of a map, because in this case it's not the same. In this general case, there is a work with Loic, where generalize the Lamperti transformation to Rn and use the Markov additive process, but that define it in different sense. But I think it's the idea behind to give this, but I'm not sure how to do it. Intersection. Well, in that paper, I'm sorry. Yes, well, two things. The first one is in that paper in the general case with Rn. I'm sorry. The one-dimensional. I think I know. I don't know that paper. What is? to obtain the Lamperti transformation in general, you mean? Yes, well, and the paper would generalize the Lamperti transformation. We can obtain this one. This one, in fact, well, I say we can recover this result in the yeah yeah. But I think in that paper is not considered the recurrent extension, right? All stable process. But related with the maps. Okay. But with the maps, yes. But recurrent extension, I think no. I don't remember if they mentioned something.